Hi, pre-calculus students. Welcome to section 1.9, the last section we will do in chapter 1, called inverse functions. You've seen inverses before where you have been given a set of points and you switch the x and the y, or you've been given an equation and you switch the x and the y and get the y alone. Why would we do this? Mainly we would do this if we've been offered inputs and outputs and we're more interested in the values of the outputs. You know, for instance, if we were talking about the lake levels of Lake St. Clair and the different dates that happened on, we might be, you know, so if you had a date that you could input, you would get out a lake level. There's actually a chart of this since 1900. What if you were more interested in, and if you had a certain lake level, what dates that happened, right? If you switch the input and the output. So what we are concerned with this time though, is instead of mainly the word inverse, we are first concerned with the word function. If we switch the input and the output for each new input of the inverse, is there one output? So we want to make sure that if we wrote an inverse function, it wrote an inverse that it is a function before we write the inverse. And in fact, if it turns out that if we wrote the inverse that it's not a function, then we will simply not write it and say the inverse is not a function. So you've seen this before, but again, it's important to refresh. So inverse means, I'll go on this side, inverse means you're switching the input and the output, which also means you're switching the x and the y, which means you're switching the domain and range. In function notation, it means you're switching the x and the f of x. And if you have written an inverse function, then we still use the name, the symbol of the original function, and we put a -1 for an exponent on the f. And that indicates we had an original function f, and we wrote the inverse of that. If we had original function g, we would have g to the -1 of x if we wrote the inverse of g, okay? Again, but these are inverse functions, key word here. So you must check first to see if you wrote the inverse, if it would be a function. So how do you do that? Simply, if you have a numeric list, the y's do not repeat, right? So for a function, the x's don't repeat. So if you're looking to write the inverse, you have to make sure the y's don't repeat because you would be inversing those. If you look at the graph of the original function and it passes a horizontal line test, again, if you remember, if you've been offered the graph, a graph of an equation and it passes a vertical line test, it means it's a function. In this case, if your original function passes a horizontal line test, meaning it only hits at 1 point or less, then that means the inverse would be a function, okay? And if there is no inverse function, it doesn't pass either of these tests, then you do not write it. You don't try to write the inverse, okay? Now, a little bit more, a function is 1-to-1 if it also has an inverse. So meaning if it's a function, then for each x, there's only one y. If it has an inverse function, that also means for each y, there's only one x, and that is called 1-to-1. Okay, so if an inverse function exists, then how do you write it? So if it's just a set of points, like we'll look at 38, all you do is switch the x and the y, and you have the inverse chart, okay? If it's an actual function, symbolic form you've been given, then you make your f of x equal y, you switch the x and the y, that actually is the inverse, but we like the y alone. And then when we're done, we'll say, you know what, our y really is the inverse function. We'll get back to our function notation, okay? How do you verify if two functions are inverses? So what if you've been given two equations, two symbolic forms? How do you know if they're inverses of each other? There's 3 ways you can do it. First of all, graphically, if you graph both of the functions they gave you and the y equals x line, and they are symmetric over the y equals x line, they are inverses. Also, if you take your original function and compose it with the inverse function in it, wherever you see an x, right? We did composition of 1.8, and you get in just an x out, they are inverses, or you don't have to do both. If you take the inverse function and wherever you see an x, compose the original function into it and get an x out, in either case, you only need to do one or the other and not both, then they are inverses. Meaning that when you take one of the functions and compose the other in it, they totally undo each other. So you just have an x left and they must be inverses. Another thing you can do is simply take the first function they gave you, write its inverse yourself, and see if it's the other one they gave you, if you're comfortable with that. So let's do some examples. I'm also going to do, after we do these, number 70, 68, and 30 from your book. But my first question is, for these functions given below, is there an inverse function if we wrote it? Okay, so f of x equals x cubed, we know what that looks like. So let's go ahead and do a graph and do a horizontal line test. So let's take a look. We know how to graph y equals x cubed. There it is. Does it pass a horizontal line test? Which would check each of these horizontal lines represents a y value. And if it only hits at one point, that means it only has one x with it, meaning there's an inverse function, right? So y cubed does pass the horizontal line test. So yes, it would have an inverse function if we wrote it. The square root of x looks like this. We did tons with that on 1.7 in our activity. Does this pass a horizontal line test? Yes, it does. It only hits at 1 point or less. How about f of x equals x squared? We know what that looks like. There we go. Does this pass a horizontal line test? Everywhere? No, it does not. It passes a horizontal line test here and here. It passes a horizontal line test here at the vertex because it just hits at 1 point. It certainly does not above here, so no. Believe it or not, x squared. Could you write the inverse? Sure you could. Is it a function? No, so we don't write it. The absolute value of x, you know what that looks like. We've worked with that. There we go. Has this V shape. Does it pass a horizontal line test everywhere? No. We would not write an inverse. There is no inverse function. Number 38, they are asking you to make a chart of the inverse. Notice that this function, that the x's don't repeat and neither do the y's, meaning this chart represents a function on its own and plus its z. Meaning also, because the y's do not repeat, its inverse would also be a function, and we could also call it 1-to-1. So I'm not going to take the time to write it out, but what would the inverse function chart be? You would simply switch the x and the y, right? We'll get it started. And you would have x, and now you would say, oh, this is the inverse, right? And our first point would be a -10, 3. -10, -3. Our next point would be -7, 2. -7, -2. I keep forgetting to say the negative, and on and on. It really is that easy. You just switch the rows. That's it. Number 41, for this graph, is there an inverse function? No, there is not. It does not pass a horizontal line test. it hit at more than 1 point when we drew a horizontal line, meaning for this one y, there's 2 x's, not an inverse function. I'm going to erase. So you may want to pause me if you're a little behind, and we're going to do 70, 68, and 30. So what they're asking for on number 70 is if this is a Q here, that is a function. If you drew it, it would pass a vertical line test. And they want to know, does this function have an inverse function? And if yes, write it. Okay, so what I'm gonna do, I always check with graphing first. Do I know how to graph this? Yes, I do. From 1.7, right, our transformations. This is a parabola that has been moved right 5. It looks like this. Does it pass a horizontal line test? No, it does not. And I would literally say that there is no inverse function and I would not write one. Nice, huh? Of course, on number 68, I made sure there is an inverse function, right? Okay, so number 68 is the same question. Would there be an inverse function for this function? And if so, what is it? So just notice for this f of x that I could rewrite it as 3/5 x plus 4/5, noting that this is a line, y equals mx plus b, right? And so if I graphed it, right, my y-intercept would be 4/5, like about right here. And then it would have a positive slope, right 5 of 3. Right. And of course, this line you can see would pass a horizontal line test. And so, yes, it has an inverse function. So let's go ahead and write that. How do we do that? Okay, I'm going to erase right here since we said yes, there is an inverse function, and we're going to write it. Here's what we can do. The first thing we do is we make our f of x a y, simply because it's easier to move things around that way. The next thing you do is switch the x and the y. Nothing else with it, just the x and the y. That, in fact, is the inverse, but we like the y alone. So I'm going to multiply both sides by 5. I'm going to work to get this y alone. Notice I'm going to have to multiply both sides by 5, subtract a 4, divide by 3. That's what I'm going to be doing now. There we go. Multiply by 5, subtract a 4. Divide by 3. There we go. There's our inverse function. I could definitely write it with a common denominator. You might see that in the book, but we're absolutely right. And we're going to remember that what we actually did was write the inverse function. Okay, got that? Number 30. Okay, just making sure I wrote it right. Okay, so they give you on number 30 two functions and they ask if they are inverses of each other. Again, as I said on number 5, there's 3 ways to do this, okay? The first thing we can do is graph f of x and g of x and the y equals x line and see if they are symmetric over that line. Now, I feel that you could probably draw 1 minus x cubed on your own, but I don't feel like you have internal knowledge of the cube root of 1 minus x. So I would think if you're going to prove that these are inverses of each other graphically, that would be okay to use a calculator. So what I did, I put f of x on a y1. I put g of x on a y2. And on a y3, I put the y equals x line and I bolded it so I could see it really well. So here's what happened when I put them on my calculator and I graphed it. See if you can see this. There we go. A little bit, there we go. There we go. So notice that I have both functions and the diagonal y equals x line. And if you folded on that line, that the two graphs would match up. So that is one way to prove that these functions are inverse functions of each other. Okay, another way to do that is by composition, meaning if I do f composed of g or g composed of f and simplify, if I just get an x out, everything else cancels. They are inverses of each other. Let's try f composed of g. Let's try this one. I'm going to write my f, right? We learned how to compose, nice and big. Wherever I see an x, I'm going to put g in, right? So I'm going to erase and use parentheses. There we go. Notice it is f. It's 1 minus something cubed. I just put g into it. Notice that the cube root and the cube cancel. Now be careful here. This radical sign is in parentheses. So I really have 1 minus x. And when I distribute my negative here and here, I get 1 minus 1 plus x, right? The ones cancel. These two functions must be inverses of each other, since when I composed them, I only had an x left. The last thing you could do, and again, you don't have to do all of these, just one of them, okay, I'm going to erase to give myself room, is I'm pretty good at writing inverse functions. I think we all are pretty good at it. So what if I just took my f or my g and wrote the inverse myself and checked to see if that's what I have? So let's work with g, right? Let's go ahead and do that. Let's say I was given g and they asked me to write the inverse function. Let's go ahead and do it. Pretend like they didn't even give you f, okay? We make our g a y. We switch the x and the y. And let's work to get the y alone. Let's cube both sides. And the cube root and the cube cancel. And we have 1 minus y. Let's subtract a 1 from both sides. To get the negative off that y, let's go through and multiply everything by a negative. Okay, and let's say that y really is an inverse function. Well, let's go ahead. What was it that we started with, g of x? Here we go. And if it's okay with you, I'm going to put the positive 1 in front, followed by a minus x cubed. And then I just check. check the f of x they gave me. Did I just write what they have? Yes, I did. F must be the inverse of g of x, because when I wrote it myself, that's what I got. So I hope you have a great day. Thanks for watching.